Testing 1, 2. Okay, all right, good afternoon. Welcome back. Any question for last lecture or not? Okay, if not, I got a question for you. So how to find the limit of the sequence here? Does anyone know what's the limit of this sequence? Huh? 0, 1, 0. Okay, I hear more 0. So how do you get 0? Okay, so wait, let me. So this is 0. So you view it as a real value function. Since sine is continuous at 0, so you can bring the limit in. And the sequence here converge to 0. Sorry, I should change this to x first. Okay, pi over infinity is 0. So you get sine 0, which is 0. Okay. And actually, really, there's a faster way we can skip this. So, okay, wait, let me finish this first. So, since this is 0, imply that the discrete version of the function also have limit 0. Okay, so this is the very first tool we got when we introduced the definition of limit of sequence. And actually, we reminded by your friend, I forget what's your name. What's your name again? Huh? Ziqian. Okay. Ziqian. So reminded by him, actually we introduced another theorem afterward, which is the sequential continuity. Okay, sequential continuous. So if limit n to infinity and n equal to L, and Fn plus L, then Fan equals to Fan. So taking limit of Fan is equal to FL. That right? That's the right statement we saw last time. So this is the sequential continuity. Okay. Continuity. All right. Okay. So right. So in this case here, so how do you apply this theorem here? Okay. How do you apply this theorem? Say again. So pi over n become your sequence here. Okay. So let me read out. So pi over n become your sequence here. Zero. And what's your f here? Your f is your sine. Okay. So this means that if you apply your function on the sequence, okay, and then you take the limit of that image, you exactly get FL. Okay, so you could, in principle, under this theorem, to compute the limit, the discrete limit of Fn, and you can actually bring in the limit because sine is continuous at 0. Okay, so let me move this stuff over. Okay, equal since uh, sine x is continuous at 0. Okay, so now we have some convenient to use here. Okay, so you can bring a limit in because the limit is continuous. Okay, so you will like skip extra step to write this continuity of the real value function. Okay, but make sure when you write down this equality here, it is when the function is continuous. Only you can do that. Okay. So make sure you can differentiate when you can bring the limit in when the function is continuous, or when it is linear, which is combination of convergent sequence. Okay, so you need to differentiate between these cases. Do you understand? Understand? Any question? No, so far no. Please let me know if I go too fast. Okay. Um, so that I know where you guys stuck. Because sometimes maybe something seems obvious for me, not obvious for you. So try to voice out, let me know, and then I will talk more. Okay. Hey, so maybe do a little bit small summary and maybe some add-on. So how to check for series conversion tests. So what have we learned? Okay. So we got the first test of divergence, which says that if the infinite series converges, then the limit of the term should approach 0. Right? Okay. So this means if you want to have a finite sum, then the term that you have should diminish to 0. Makes sense, right? Makes sense. Okay. So we also prove it as well. Already proven. So this one proven. Second, what have we learned? I think it's the integral test. Right. Integral test. What the integral test says? Start with f that is continuous, positive, and decreasing. Okay. So if the integral of 1 to infinity of fx dx converges, then the discrete version of the summation also. All right. Okay. So there's one reminder for this test here. The one here doesn't really matter. Okay. What matter is you need to start with the function which is positive, decreasing, and continuous. So for example, okay. So for example, if you have done exercise, you should have seen this question here. Okay, ln x over ln n over n. Okay, so ln n over n, the graph looks something like, let me sketch, something like this. Okay, so meaning it increasing at first, but decreasing at some point. About 3 and 4 it decrease. Okay. So meaning you can only apply this theorem starting at 4. Okay, when n equal to 4, right? But does this affect the convergence or not? No, right? Because because if it converges, then you add 3 more finite terms is still a finite term. Make sense? Okay, of finitely many terms, I mean. Okay, so this one here doesn't really matter. What's matter is when is it decreasing? Okay, positive, continuous, decreasing. Okay, make sense? Okay, sure. Okay, feel free to stop me. Okay. Uh, what else did we learn? Okay, I think we learned geometric series. Okay, a specific for specific um series. When does it converge? So this is what Rn A converges. You can only if the ratio is less than 1. Is that right? Please check. Okay. For P series, what's P series? P series is the one that is taking x, wait, let me think, n to the power of, okay, converges if and only if P is greater than 1. Okay, good. Okay, so these are specific one. What else? Comparison test. Comparison test. What does comparison test do? So when you have uh, two positive sequence and one bound the other, if the series of Bn converges, then the series of An converges. Is that right? Is that right? Okay, so above converge, then you push it down. So let's prove this. Let's try and prove this. So yeah, let's try and prove this. Okay. So what we're going to use is what are we going to use? So let's prove this. So suppose Bn is converging. Okay, is convergent. We want to show that An is convergent. So we want to show that the different series of An converge to a finite sum. But we already know that we already know what? We already know that the series of Bn converge to something. Maybe we call it P in this case. Okay. And then we try and fix some partial sum for the infinite series of An and the infinite series of Bn. Okay. So we have 3 objects here. So we have partial sum for An, series of An, partial sum for series of Bn, and then the sum to infinity for Bn because it converges. Okay, so we're going to find whether Sn converge or not. Okay, so note that for both of them, they are positive sequence. Okay, in particular, since every term is positive, then your Sn and Tn is non-decreasing. Okay, because either you add 0 or either you add some positive number. So the partial sum is always form a non-decreasing sequence. Make sense? Okay. Okay. So so we got the limit of Tn is equal to T because it converges to some number. That means the partial sum converges. Okay. So not that this Sn, right? Sorry. This Sn here, okay, is bounded by T. Okay, why? Because every AI is bounded by Bi. Okay. Similarly, the partial sum will be bounded. Okay. And then if you take Tn to infinity, then the T will bound every partial sum. Make sense or not? Make sense? Okay. So in this case, we found a monotonic and bounded sequence. Okay. Sn is non-increasing and then it's bounded by this limit of the infinite series of Bn. Okay, so it is bounded, it is monotonic. So by monotonic sequence theorem, An, the infinite series of An is convergent. So the idea here is show that the partial sum for the An form a monotonic monotonic bounded sequence. Okay. So far, okay. Any question? Any question from the back? No? Okay. Some of you look a bit confused, I mean. Is it okay? Okay. Okay. So actually, I've already pulled out the proof, and in the last lecture, I just want to bring it up today. Okay, next, there's another test we learned, which is what? The limit comparison test. What's the limit comparison test? Okay, so you also start with a so we also start with two sequence, A and Bn, which one of them we want it to be strictly positive. Okay. And then we look at the limit over An over Bn. So the one that is strictly positive will be lying in the denominator. Okay. Usually this is the one we want to prove whether it's converged or not. And then in the denominator one is the one that are known. Okay. So the theorem is if you found out the limit is some finite number, then the two series either converge or diverge together. Okay. So if you know that Bn converge, then An should converge. If you know that Bn converge, I mean infinite series of Bn diverge, then the infinite series of An also diverge. Okay. So if you found that L is 0 and Bn converges, then the sum of An also converges. Okay. So last time also we didn't prove this, so maybe is worth for proof. And let's quickly prove this. So okay, so what's the idea here? What's the idea here? So the idea here is we are trying to make use of the number fifth test, which is the comparison test. Can we bound an by something? Okay, can we bound an by something? Okay, so we will prove the first one first. Okay, let's prove the first one. Okay, since L is finite, okay, so we can find some, there's this some M and M in maybe R, such that M, little m is less than L, is less than capital M. Okay. So what's the definition of limit? Okay. What's the definition of limit? I mean, we don't introduce that definition in our class. So I think you study in calculus one, is it? Okay, but sure, okay, never mind. But if you use that, it's good. But so the principle is for large large enough n, for n large enough, we can make sure that an over bn is less than m, is greater than small m. So make sure meaning if you want to go into details, you can use the epsilon delta definition. Okay. If not, then this is the result. So with this result, we can show that actually an is bounded by capital M times Bn and bounded below by m times little m times Bn. Okay, so in this case, you can see that if Bn converges, I mean infinite series of Bn converges, then as scalar multiply Bn also converges. So there are two steps here. So scroll down. So if the infinite series of Bn converges, then a scalar time your series also converges, right? This is the property of convergent series. Okay. Then by what? By the comparison test, the series what? An also converges. Okay. So if you can see that, you also can see that if Bn diverges, little small n times Bn, the infinite series defined by little small n times Bn also diverges. So you are greater than something diverge, so you also diverge. So let me write down. So if the sum of Bn diverges, okay, we make full use of the other inequality, and then we see that the little small n times Bn define a divergence infinite series. Then by comparison test again, an, the infinite series of an diverges. Okay. Do all of you agree? Agree? Okay, good. Okay, next. Next part is how about if limit is 0? Okay. What does it mean by limit to be 0? Okay. We could say that Bn is greater than An, right? So you want something very big in the denominator, so that, or something very small in the numerator, so that this limit go to 0. If you want to show it rigorously, you can use the delta epsilon. So this implies that An over Bn could less than 1 or large n. Okay, because it's keep approaching 0, right? In particular, you can find some number that's such that An over Bn is less than 1. If you cannot find it, then your limit won't approach 0. Another way to see it. So in this case here, we form a inequality between An and Bn again. Okay. So in this case, comparison test again. So if Bn converges, then by comparison test, the infinite series of An. So that's why in this limit conversion test here, we have these two extra conditions together to make sure our An infinite series of N converges. Okay, make sense? All right. I think we have the last one that we learned before we take a break last time, which is the alternating series test. So this apply for alternating series. Yeah. So you should start with an alternating series. So if you have a alternating series, okay. So let's write down the alternating series. It's actually alternating -1 with some coefficient Bn. So for example, this Bn appeared the wrong place. B1 minus B2 plus B3 minus B4, so on. Okay. So we try to split up the coefficient -1, the sign with the Bn. Okay, such that Bn is always positive. So two conditions to check on Bn. Okay, first of all, it is the non-increasing. Okay, it's non-increasing. So first of all, it is non-increasing. So we write down. Second of all, it is diminishing. Okay, diminish to 0. Okay, so every term must diminish to 0. So surprisingly, these two conditions is enough to deduce that our series is actually convergent. So these two conditions is enough to check whether an alternating series convergent. I think there's one more. Okay, one more. There's actually the absolute conversion test. Okay, so what's absolute conversion test? If you consider the modulus value of your terms inside the series, and that infinite series converges, then the original series converges. Okay, so try keep this test in your mind, at least for this course. Useful. All right, any question on these tests? So for some of the question, right, maybe some test is obvious than the other, so there's no fixed answer for one question. Okay, so please be flexible a bit. Okay. Next, so we'll keep going. So we'll start new stuff today. Okay, new material. Okay, so yesterday we talked a little bit about rearrangement, but here the rearrangement means if you want to rearrange the infinite series, we mean that a series obtained by simply changing the order of the terms. Okay, so this is within a series. Okay, we want to change the order of the term. The order you add them. Okay, so we will see in a moment why this matter. Okay, so there's a theorem here. We won't prove it. So first theorem is if AN is an absolutely convergent series with a sum x, then any rearrange of the infinite series has the sum x. So what's absolute convergent means? What does absolute convergent mean? The definition doesn't say equal or not. They just say the sum of AN converges and the sum of absolute AN also converges. Okay, so for both these two converges, and then you found that the sum, because it converges, right? So you can find a sum for it, sum to infinity. Then if you rearrange, no matter how you rearrange it, you still get the same sum. Okay, this is the point. But in the second case here, if AN is conditionally convergent series, okay, so meaning what? Yeah, meaning is not absolute convergence means what? Meaning uh if you, for example, one example of conditionally convergent series, you should think about alternating harmonic series. Okay, so if you take the absolute value and then you do the infinite sum, it doesn't converge. Okay, so you should think of it. Think of the alternating harmonic series, and this theorem is quite strong. And if R is any real number, okay, then there's a rearrangement of AN that has a sum equal to R. So meaning you can rearrange such that you get any number R. It literally equal to any real number. Okay, it's just using the same series but different rearrangement. I think somehow this is quite surprising. So we'll see the example. So let's say we have an alternating harmonic series. Okay, it can be shown that this sum to log 2. Okay, so you need to add in this way. Okay, 1 minus half plus third minus half plus fifth. Follow this order, and then you get log 2. This is an exercise in the textbook, I think. If you are interested, you can look for it, or you can try and prove it yourself. If we multiply, we do some manipulation to this series here. If we multiply by half, okay, and then we plus 0 alternating 0, and then we apply to both sides, then we'll get this equation here. Okay, and then what we do is we add the two series. So we add 1 and 2 together. Okay, what happened is we get back our alternating harmonic series again, but with a different order. So you can see that we go from 1 to 1/3, and then go back to half, then continue with fifth, 7, and then we go back to 4, 1/4. Okay, so it can be shown that actually this is also this is a rearrangement of alternating harmonic series. Okay, but the number on the right changes, become 3/2 times long. Okay, long 2. So this is just an example. If you're interested, you can try and prove it. Make it your assignment project. Yeah. Any question? So this is the rearrangement theorem. So be careful when you rearrange the sum in the conditionally convergent series. Okay. But for absolute convergent series, you are fine. Okay. So far, okay. So far, so good. Okay. So let's continue. Okay, next, the ratio test. So last time I got feedback from some of the classmates. You're confused with this A N B N here. I think when I first learned, I also confused, just that I forgot already. So yeah. So when you first see this limit comparison test, right? Because why? I know why you confused. Because most of our series is like something over something, right? It's a fraction form. So you think of it like splitting the fraction into AN and BN. Okay. But actually AN and BN in the limit comparison test and what? Comparison test is coming from two series. Okay. Now the ratio test we are going to introduce is coming from one series. So you see the name. We will put AN plus 1 as AN instead of BN, CN, DN, so on. Okay. So, uh, so in the ratio test, what do? We start with a single series. Okay, we start with a single series. Okay, we start with a single series, and then we check AN plus 1 over AN. Okay, so meaning we check the next term with the previous term. And then what's the limit of this ratio? Okay. And then we check on the modulus of it. Okay, check the modulus of it. So if this limit is less than 1, okay, then this series converges absolutely. This series converges absolutely. If the limit is greater than 1 or going to infinity, this series diverges. If it is 1, we don't know whether it converges or diverges. Make sense? Make sense? Okay, let's try it out. So let's try on this question here. So this is what? This is an alternating with power 3 on the numerator and then n factorial in the denominator. So that this converges absolutely. What does it mean by converges absolutely? The modulus of the Bn, the infinite series defined by the modulus of the Bn converges. Okay? But ratio test will give you this condition if you check that An plus 1 over An plus is equal to some number that's less than 1. Right? Okay. So does everyone know what we want to do now? Okay, we want to compute this limit here, whether it is less than 1 or not. If it is less than 1, then it converges absolutely. Okay, let's try and do it. I think the first, usually the first method I would use, I guess, is this ratio test. I think ratio test is quite useful most of the time. So I would recommend this ratio test for the first try. Okay, so compute this. So what's this? What's this? How to simplify this? Right. Okay. So we can slash out the n, and then what we left is 3 over 3 plus 1. Right. Then what is this? Is it just, since everything inside is positive, I can throw away the modulus. So yeah, 0. Okay. So 0 is less than 1. So it falls into the first case here. So it converges absolutely. Make sense? Okay. Okay. I think not that this also can be solved using alternating series test, right? Yeah. Okay. If you want, you can try write out the alternating series test. So, and then you compare which one is faster. I always compare which one is faster. Then if you do more and more, then you get a feeling. And then you get a feeling, then next time you see similar question, then you know which one to use. Okay. So by the ratio test, series converges absolutely. Okay. So okay, I'll let you try this. Spend about 3 to 5 minutes. Try and do this. Check whether this converts or diverge. Okay, so you set out the an plus 1 term and the n term, right? Does anyone get what the limit is? Anyone get what the limit is? E, yeah. Okay, good. So let's see how we get E. So really, this negative one, alternating negative one, right, disappear under this modulus, right? You really don't need to care about it. So how to compute the rest? So you rearrange nicely Okay. And what do you get? So you will get, oh, am I doing something stupid? Let's keep going. N+1 over n to the power n, and then n+1. Okay, good. So then you can cancel out one of the n+1, and then you will get. So since we already get rid of the modulus, right, and then inside are all positive, so we just remove the modulus, which is n+1 to the power n over n to the power n, which is, you can bring the n inside, plus 1 over n to the power n. So this is the famous limit, which is equal to e. Okay. I don't think you can solve this by just bringing limit to something beside n. So this has to be solved. I forget how to solve it, but some trick need to be used to solve this. Okay, so if you're interested, you should go and find out why this limit is e. I don't think it's hard. Just some trick you need to use. So since this limit is greater than 1, so based on this list here is the second case. So the series diverges. So by the ratio test, the limit diverges. The series diverges. Okay. I think we are not going to prove the ratio test in the class. So if you want to do it, you can do it in the project. Should we take a break? Let's take a break. Let's take a break until 11:59. Yeah, 11:59. Let's take a break and then we'll come back.
So if they returns out less than 0, bn bigger than 0. The result C and the result bn are convergent. We can get the result A are convergent. A proof.
But this is the proof?
Yeah.
Let me see. So it's correct.
Yeah.
And then what do you do? So you want to show that this converges, is it?
Yeah.
So that.
Because C and bn are convergent.
Why you need both? I thought you need one is not. Oh, you mean this plus this?
Yeah.
Or this plus this? Does it
No, it's
less than one of them? Maximum of them?
maximum. Positive is negative. So So we should choose another example, another rule to
Another rule?
to
I thought you just add them together.
yeah.
Huh?
So so all 我用中文说行吗？
说
可以得到一个这样的必然去考虑它是不是抗日人。如果它是负的话，或者说选一个另一个标准去衡量它。
没有，我的问题是为什么你不能够用这个就好，为什么还要用这个？
因为我不知道它就是它可能
可是
对啊，但如果它右边的绝对值大于 c 的，
但是我觉得也不能够这样把嘛，我觉得你要把他们两个加起来才可以。我觉得他们两个都不够吧，他们单个的时候，我觉得就是就是不够吧，我觉得，我觉得这个是不对的，我是这样子，我觉得没有，你就算选一个大的，他也帮不了，觉得是他们的三才能够帮。对啊，我觉得，因为你是怕，因为你是怕，你怕减的时候，可能它这个 value 会大过上面的 value，对不对？
对，
但是如果这样的话，你怎么可能可以说，就是说，如果拿他们三的话，就意思说我就可以用另外一个来帮助这一边，然后另外一边我就用这个来帮助它。虽然我加了另外一个东西，但是这两个都是 conversion，我加起来还是 finite，
嗯
懂什么意思吗？
嗯
啊，所以说，OK，
嗯，
我觉得这个是一个 special case，这个 special case of Swiss 人对不对？对，这个 special case，对，然后
其他情况，我觉得就是要么都是在上面，要么都是在大于零，要么都小于零。然后，然后在这两个那个 series 中间还存在一个 series，它是 convergence，
什么再说一个
就说对，这是那个 x 轴，然后
嗯哼，
这个也是 那个 series 下的 convergence，
那为什么为什么你的这个 CN 它可能可以跳啊？
对啊，可以，也可以调，
对，也可以跳，它不一定要完全在上面，它可以一下在上面，一下在上面，一下在上面，一下在上面，也可以这样。
嗯，
对对，
对，不会这样，
什么？
对，不会这样，
微正
嗯，
没有啊，明就是要想，要想，
但我感觉就我没找实际过来，
对，
就那个 counter example，我发现它不符合这个，要么是它的两个 bound 是 convergent，
嗯，你说你想不出来他们的
对
怎么？
convergent，对啊，
就我的想法是这样啊，就是说，当你在造那个 content example 的时候，其实你就是在想怎样，一的是怎样破解它，一的是怎样 prove 到它，
嗯
懂什么意思吗？
嗯，
如果 CN 全部是 positive 的话，我们其实证过，
对
其实就是那个什么 comparison
对
test，对，所以应该最麻烦的是它一上一下，一上一下，
对，
嗯，
嗯
你看一下那边能不能找到一些漏洞，你可以去 construct 一个不 convergent 的 series。如果不能的话，然后你就说为什么我不能够 construct 呢？可能就是这个原因可以让你做到。 这样子，思路是这样。
是刚才那个 confirmation 你的 proof
啊
所以那边你是写他们两个都不让你分析。
，OK，
用 decreasing 的话，就代表它就是要么升，要么就是停着，就是
嗯，
升，要么停的话，它
喂，
就一定是
对，
它就一定得为什么是？因为
但是因为它 bound by 一个东西嘛，对啊，它一定 diverge，但是它 bound 住嘛，所以才有到这个 monotonic sequence theorem，因为它 被 bound above。
然后那可是你还是继续加这个，你是一样大于的，
对啊，你一直加它，所以它意思是说你一定会停在某一个地方，这个monotonic
哦，整个 sum 是整个 sum
整个上
啊，整个 sum 包的一个号码，对，
它就是帮助它一直上，所以它一定要停或者它 approach 一个东西这样。
可是如果如果你那个只是 term 的话，是的，
turn by turn，
如果你就是讲 term by term
turn by turn，
你一定是要 decrease 是不是？
你就想说觉得是 C 的是啥？
什么东西？
就是因为我刚才想到的是你的整个 sum 它 bound 是被 bound 一个点，
因为
对
三 B 是convert，所以 B 也是会跑去零嘛，所以 A 被包的也是会 service 进去零。
对，可是这一点，
跑去零没有啊，没有说 P 会跑去零，
可是
没有说 P 跑去零，没有说 P 会跑去零，不一定诶，应该不一定。它这个是 partial sum 的 sequence 是 non decrease。
三 B convert，所以我觉得 B 会 convert 去零。
啊，对，OK 对，OK 好，可以，
对啊，他讲他会跑去别的数。
跑去别的时候。如果 suppose BN 是 convert 啊，对，第一个 test of，呀，
我就被那个 not decrease 那么
OK，hello，yeah, before we start, I can open Moodle today, so I put the information under this course information document here. So I lay out some guideline here. So please write about 1.5 full page content. Content meaning without references. Maximum 3 page. No need too long. And then should be explaining some theory in detail and efficient. That makes sense to everyone here. So meaning if I pass your paper to your friend, they should be able to understand it. Okay, so I don't want you to write something hard. I mean, something not readable or copy from somewhere else. So you must use your understanding and write it out. So when I pass to your friend will get some knowledge out of it. Two is your personal interest towards mathematics subject. So you are interested in that topic, you go and find it, you can search for it, read it, understand it. Okay. And then to fill in the rigorous gap in the theory presented in the lecture. So maybe some of the theorem we don't prove in class. Even textbook you cannot find it. Textbook go and refer you, so you go and refer it. So try and present that thing. Okay. If you need extra definition, then you need to introduce it. Okay. Even though it is not introduced in our class, you can introduce it in your paper. To learn, read, learn and find mathematical references and research papers. So you look at the paper, if the paper refers you to another paper, you go and read another paper and then you keep reading, okay, until you get the whole theory out. So project recommendation. So one of it is if you want to prove some famous theorem, proven theorem, is major theorems or result we use, you can prove it. For example, I'm not sure this is long enough or not, but we didn't prove it. Because maybe need epsilon delta stuff, I guess. And second is originality is, for example, you're interested, for example, 你叫什么名 What's your name? 啊，李谭，李海 What's your surname? 啊 What's your surname? Uh, first family name. Li, Li. Or Li Kai. Okay, just to get Li Kai. For example, Li Kai interested or pass the so interested in some whether he is interested in produce some condition to prove some series converge or not. Also can. If you like, you can prove your own lemma which is not been proven. Third is foundational issue. So for example, we don't discuss about completeness of real number, construction of real numbers. If you want to write about those things, also can. This is just example. Okay. And let me see. So if you also think of other topic, you should talk to me. Make sure you talk to me, okay, before you write. So structure will be introduction. Okay, so you need to talk about history, how this problem come about, and some background about that problem, and then set out the theory. So you need to introduce enough definitions so that you can prove stuff, can present the theory, okay, and then prove. And then definitely they want the theory because they want to show it on something. So you need to find some example such that the theorem works. For example, if it is monotonic conversion theorem, then you need to show me sequence which is monotone and monotone and bounded, and then use this theorem and then show me why this theorem tell me it is convergent. And then of course you need to write down all the reference you use. So marking criteria break into language, completeness of argument, presentation, and difficulties. Okay. So how complex or originality of your argument. Okay. So if you wonder about the references used, right, you can refer to the paper on my website, the paper written by me. Okay. Yeah, you can read those. You also can read those how we write a paper. For example, the abstract and intro. You don't need to read the detail, but read the abstract and introduction. Okay. So you should be able to understand the storyline, but not the subject itself. You get what I mean or not? There's a lot of words you don't understand, but you should be able to understand the storyline. You get what I mean? You get what I mean? So, okay, I'm teaching you a technique is you read a passage, you don't know what's the subject, object inside, but you can get the storyline out. You get what I mean? Okay. So even though you don't know that specific word, but you should be able to follow the logic to get the story out. Meaning you know how to connect that two things, but I don't know what the two things are. This is what I meant. Okay, this is the skill you need. You don't know what I'm talking about, but you need to know how they are connected. Okay, so you can start by reading my paper on my website if you like. And all other mathematical reference work like that. Okay, you can read the paper. You don't know what subject they are talking about, but you should know how things are get connected. Okay. Okay. So most important thing is no plagiarism. Plagiarism between students or plagiarism copy from some website directly bought the paper, copy paste. Yeah. These are all plagiarism. So rephrase and write in your own word. Okay. Not I don't need you to write hard stuff, but you need to write such that people understand, especially your classmate. Okay, actually the second project I have the topic in mind, but I haven't write out the real detail. So it's a real life application of mathematical theory. So these two topics potentially they could have connection. So meaning we write about this theory, how we use in maths, and then why they care about that equation because of really real life application, physics application, biological application, chemical application, or what. Okay, so this is the second second project. Okay, if there's no connection, that's fine, but you could make it such that there's connection between these two. But if it is not, never mind. Okay, yeah. So second project will be more to real life applications. So you talk about real world problems, and then you will present this. Okay, so this is coming soon. Third month of the semester. It's coming soon, but please work out this. No one see me in the office hour yesterday. Okay, I will have office hour today as well. So after this class, which is 1 to 3. So if you have anything to discuss with me, you should come and meet me in my office. Okay. Okay. Any question for the project? Yeah. Where's my website? You can search my name. Yeah, search my name. It's a Google site. You can search my name. Found. So you can read maybe a thesis or the paper or the research statement I wrote. Yeah. See if you can understand the storyline or not. Okay. Maybe there's a lot of vocab that you don't know, but see if you can follow the story. Okay. Let's continue. So continue root test. So root test meaning you need to take roots. Okay, so this is convenient when your sequence have some power n. Okay, there's power n increasing. Okay, so let's come back to our lecture first, then you will find your research later. Okay, so for root test, you also start with a series. Okay, you also start with a series, infinite series, and then you consider the n root of the modulus an. Okay, similar result you have. If the limit is less than 1, the series converges absolutely. If it is greater than 1, the series diverges. If it is equal to 1, you cannot decide. Okay. So let's use it on this test here. So for example, so just set up the limit test. So you take the modulus of your term, and then you take your n root, okay, and then compute this. So what's this? Really, wait, let me bring this modulus out first. Okay, so can you get rid of the modulus in this case? Can you get rid of the modulus? Yes, sir. Why? Why? Everything is positive. So you take positive power over positive, right? So everything is positive. So really, you can just regard it as the n root of power of n of 2n plus 3 over 3n plus 2 over n, which is just the fraction itself. Okay, up to here should be pretty obvious. What should you do? What should you do? Divide by n on both sides. So you get 2 over 3 over n, 3 plus 2 over n. Okay, so this thing is just converging to 2 over 3, which is less than 1. So if it is less than 1, then the series converges. Absolutely. Pretty straightforward. I think we won't prove this as well. So if you're interested in the proof, you should go and look for it. For this kind of proof, right, they usually need epsilon delta definition. So you need to read about epsilon delta definition first and then prove it. Okay, so I think pretty much for the series test. So make a summary here. So there's a test of convergence, P-series, geometric series, we mentioned before all these, comparison test, limit comparison test. Okay, so this one include limit comparison test. So maybe like 4.5 here. Limit test. Alternating test, series test, ratio test. Okay, we just introduced today. Root test, this is also introduced today, 2 of them. And then integral test is introduced last time. Okay. Okay. Should we quickly decide what test you want to use for these different series and then try and do it at home? For example, this example here, first example here, what test do you want to use? Test of divergence, sure. You can use test of divergence. I think, is a ratio test good or not? Is a ratio test good? No. Who say? You say? You think no? Why? Oh, no way? What? What? What did he say? What did you say? Nothing? Okay. Don't know. Maybe try ratio test. I like ratio test a lot, so I'll try it. Okay. Next one. What test? Limit. Okay, you can use comparison test or limit test. This is a bit like look at the largest leading degree, right? And look at the leading degree and then try and compare the simplified fraction involving n or the series, right? Compared to the P series, in other words. Okay, next. Integral, because this is like continuous stuff. And then I like ratio test. Try ratio test. See what kind of example not suitable for ratio test. I think ratio test is quite versatile, very versatile. I mean, from my experience last time, I haven't do this for a long time, but usually I start from ratio test. Okay, and then how about this? This something alternating coming. So you can use alternating series. Okay, so I write down this strategy. You should go back and test it, right? So I'll do it as well. So we will see. How about this? Ratio test. When the power, the degree, I mean, the ratio, the ratio for top and bottom, the degree of increasing is, the difference of degree of increasing is very big, then usually ratio test will work. Okay. If it is small, then ratio test might not test it. Because when the ratio is equal to 1, then you cannot do anything. Okay. So usually when they increase very fast or very slow, depend on which you see, the difference is large, then you can use ratio test. How about this one? P series? I'm not sure. Geometry series maybe, because there's a fixed 1/3 hiding inside. So maybe you try geometry series comparison test. This is like shifted geometry series. So try to start from there. Okay. Yeah. So these are just a brief sketch. So you should try it out. Okay. Yeah. Okay. Okay. Next, we'll talk about power series. So we look at this specific series here. So actually, this definition here, I should add a power series in x about x equals 0. So later we'll see how the shifted be the series. So power series means this power, right? What does it mean by the power? So the power is the power on the indeterminate, which is the x. Okay. So you start with a constant term. So here you have a constant term. Then a linear term. Okay. And then a quadratic term. And then you keep going. Up cube to the power 4, 5, 6, 7, 8, 9. Okay. So power series is the specific series. So next example is for what x does the power series converge and what is its sum? Okay. So in particular, power series is a series. So how to determine whether this when does this converges? What test can we use? Geometry, sure. So if you are using geometry series, so what's the first term? A equal to 1, x equal to, x, r equal to x, okay? So this series converges if and only if what? The absolute value of x is less than, okay? Okay, so for what x, okay, we solve this. So if it converges, it is the sum to infinity, which is equal to a over 1 minus x, okay? So what we are achieving here is we managed to write 1 plus x squared plus x cubed and so on. Natural number power of x equals to 1 over 1 minus x, okay? But this only works for x that is in between 1 and so on. Okay? So outside 1 and minus 1, we couldn't conclude this. And this number diverges. Make sense? Okay. Okay. So this is one of the important power series you need to remember. Yeah, this is very important power series. Really important. Very important. So if you sum up natural number power of square, then it's equal to 1 over 1 minus x. Okay. Next, how about this one? For what value is this series convergent? Okay, so how to check this series converge? What test you're gonna use? Ratio test, because top and bottom increases. Yeah, there's a degree of difference. Okay, let's try the ratio test. So if the ratio test need to converge, the ratio have to, if the series have to converge, the ratio have to limit to what number? Limit to something less than 1. Okay. So the series converges if the limit of the n plus 1 term over the n term is less than 1. Okay, so you need to measure this thing less than 1. So how to simplify this guy here? get Sn plus 1. We straight away do it. Okay, let's do it straight away. So Sn here slash with the n here, Sn here, and then 2n here slash with the n here. So we get n plus 2 and over 2, right? Correct? Okay, that's the one. All right. So you can see that x is an unknown here. So we don't know whether x is positive, negative, or not. But all the rest are positive. Correct? Agree? Okay. So we can just move all the modulus inside the x. Okay. Okay. So does x contain variable n or not? Okay. So limit doesn't affect the x here. So limit only affects n. Okay. Right? Because we're taking n to infinity. So what does that approach to? What does this approach to? What does this approach to? 1/2. Okay, good. So 1/2 x less than 1. Okay. So if you like, this is just 1 plus 1 over n, 2, 1 plus 2 over n, which is 1/2. Okay. So this implies what? This implies that modulus s is less than 2. Okay. So the range, if it's gonna converge, okay, just give a condition on x, which is x have to be in between 2 and minus 2. Okay. So this means x have to be minus 2, x have to. Okay. So what about at minus 2? When it is minus 2, this limit equals to what? When x is minus 2. The limit is what? Equal to what? Let me write up. When s is equal to minus 2 or 2, the limit of n plus 1. So let me write an plus 1 over an, which is simplified. We already check it. Simplified to 1 over n plus 2 x over 2. So if we start minus 2 or 2 in, what do we get? Maybe go to this stage. So what do we get? 1. Okay. So for 1, ratio test is inconclusive. Okay, we don't know whether it converge or diverge. So what to do? What to do? Try. Correct. Try. Okay. So you plug. So try meaning you plug x equals to, when x equals to minus half, what is our series? Okay, what does our series become? Okay, so our series is Sn over, let me see. Okay. Then our series considered now has a variable x, different from what we considered before. Before we only have n and number. Now we have variable x. Okay, so we need to determine whether x equals to -2. Yeah, why? Oh, sorry. Why -1/2? I also don't know why. Okay, so yeah, x equal to -2. So let's substitute this x in. What do we get? Okay, we get this series here. Okay, so what's this series here? Alternating one. Summary series. Okay, good. Because if you cancel the 2 out, we're really left with the alternating 1 over n plus 1. Okay? And this alternating start from 2. Okay, so this is what? Converge or diverge? Alternating harmonic series or converge. Okay. If it is harmonic series, it diverge. Alternating harmonic series that converge. Okay. So this one converges. Converges as it is alternating harmonic series. Check something. Okay. Sorry, here start from 0, right? Here start from 0. Okay, so we should start from 0 as well. So let's start from 0. Start from 0. Start from 0. So really we start with a right alternating harmonic series. Otherwise, we start with the first term throw. Make sense? Make sense? We start with 0. Or we just start with the wrong place, but that doesn't matter. I mean, it doesn't matter for the conversion, but for this question, it matters. Okay? Any objection? No? Okay. So next, we compute what happened next at x equal to 2. So what happened at x equal to 2? So when x equals to 2, you really get the harmonic series. So this diverges as it is a harmonic series. If you really care about this labeling, right, you also can change the starting index so that it looks like what we started with harmonic series. But they're really represent the same series. Okay? It's a matter of guess. Okay, so all together, what do we get? So we get that the original series converges when x is in between -2 up to 2, but not including 2. Okay. So usually ratio test give you the interval, and then you need to check the endpoint. Because when it is equal to 1, then it is inconclusive. You need to check. Right? Any question? No? Okay, let's try. I'll let you try this question here. Spend about 5 minutes. Try this question. See if you can find the interval. Yeah, so this is also why I like ratio test a lot. So it is used in this text as well. Have you guys looked at the assignment yet? Okay, started doing it? Not yet. Please don't leave until last moment, okay? Please don't leave until last moment. Please start. teaches the calculus one? Huh? To linear algebra? To Lin or Liu Jie? Why you guys laugh? Why laugh? What? Huh? Oh, he graduated Tsinghua. So what's so funny about Tsinghua? Why is it so funny? He said he graduated from Tsinghua. Or what? Oh no. Okay. I don't get your funny point, laughing point. How about discrete math? Oh, they run. Okay. ，Actually, I didn't know Liu Jie graduated from Tsinghua. Singapore, I think, for some time. Okay, so what's this ratio here? Anyone computed? Anyone compute what's the ratio here? What's the ratio? Huh? Oh, wait. Tell me what you simplify first. 1 over. X. Oh, yeah, X over N over N. Okay, but typically X has nothing to do with the N, so we split X and N. Right? We view X as a constant for now, constant in X, in N. Okay, so you get 0. So 0 times anything is always less than 1. So this means no matter what X you put, it will still satisfy the inequality. So this means X can be anything. Okay, it's the whole real line. So this X actually, yeah, so to be super precise, right? So I should say where this X live, okay, so that you would know that where you should be your X. It converges anyway. So this means if you put pi over n factorial, it also converges. E over n factorial also converges. So you can find the sum actually. Whether the sum is rational or irrational depends. Okay. All right. I think we should skip the next one. I think it's the same thing. So just left for exercise. Let's go homework. You guys try the homework or not? Yes, right. Okay. Did you found my mistake or not? If you found my mistake, you should let me know. Okay. I will correct it in the lecture. No? Otherwise, people read it also wrong. Right? So if you found my mistake, make sure you let me know. Send me image, just image. Send me message, email or what. Okay. Okay, next. So this particular interval, we call it what's the radius of inconvergent. Okay, we call it radius of convergence. So it is always an interval, either it is a single point or any interval, closed interval, open interval, so meaning closed on one side, open on one side. Okay, all interval we consider, and the whole real line, you already see it just now, but you haven't seen the example when it is a point, but you will see it if you do the homework. And then where's the R? So the R is you divide the interval into half. Okay, you have minus R and R. So if it is only converge at one point, then the radius is 0. If it converges on the whole real line, you divide infinity by 2, you still get infinity. So it's infinite in any case. Then the interval of convergence of a Poisson series is the interval that consists of all values of x for which x the series converges. So that in example here, either 1 point, either interval, the whole river. It's just some summary. So next is this power series here. So power series in centered at A. So we'll move the center A by taking x minus A. This will come very often in later topic when we do vector calculus. Yeah, where we move the circle, we move the line, we move the sphere away from center, then the basic graph will change using this x minus a. Okay. Okay, keep going. So this is the theorem. So why do we have such interval? Because power series always converges in an interval. Okay. So either at the point itself or some radius r away from A, okay, or a whole real line. So this is general principle, even if you shift the power series. Next, going. Yeah, so there's one remark here. What's this Cn? So you see, the remark here is if the limit of Cn over Cn plus 1 over Cn, and then take the absolute value L, actually you can get the radius out. Okay. I guess this is when it converging, so you can get this length out. Okay. So then the radius is just 1 over L. Okay. So what's this Cn here? So you should go back and check where does this Cn come from. Okay. So this Cn is actually coming from the coefficient of your power series. But this is just the what? What is this? This is just the ratio test. So they give you a general method here, but this method is really coming from the ratio test. So this is make a remark here. So this is from ratio test. Okay, so what time is it? 12:40. Maybe try one of these. Try one of these. See if you can find the interval of convergence in radius. So you use the what limit test, right? So you should set out the limit test. Sorry, ratio test. So this for this series, right? Where does it center at? Oh, good. Later on, we will see what's the rationale of this power series. maybe next week. What's this? Anyone computed? What's the n terms here? Anyone managed to simplify the big fraction there? Got 3 times x here. So what's the n terms here inside the square root? N plus 1 over plus. So what does this limit equal to? 1. So I do 1, so we get 3 over x. So we get x is less than 1 over. Right. So this is the L. This is the L that the previous remark talked about. Okay. So your radius is 1 over L, 1 over 3. Make sense? Okay. And what else? So now so let me write out first before we do anything else. So the radius is equal to 1 over 3. So which means for x in between 1 over 3 and minus 1 over 3, it converges. So we still need to check the endpoint, right? Whether it converts as well or not. So you need to check. So maybe we don't do it now. So you can keep going on. So check whether it converges at the 2 endpoint. Okay, to check whether it converges at the 2 endpoints or not. Whether you want to include the 2 endpoint, because at the endpoint the limit is equal to 1. Okay, so if the limit equal to 1, you cannot decide anything. Okay. Next. So next is a representation of functions as power series. So you can write your function in terms of power series. Okay. Do you guys know how to plot 1 over 1 minus x? 1 over 1 minus x. Do you know how to plot it? Yes. So you know how to plot 1 over x, right? Correct. So 1 over x is like this side and this side. So minus become the other side. Okay, and then you shifted by 1. So you shift to here. Right. Okay, so let's have a sketch. Or maybe something like this. Okay. So this means that when x is around 1 and minus 1, so maybe around here. Okay. The graph can be approximated by this curve. So you can make 1 and then x and then x squared and then s cubed, so on. Okay, to approximate the graph. Did I draw the wrong graph? I feel like I drew the wrong graph. But anyway, but the point is you can add out this graph at this point to approximate all the point here in between minus 1 and 1. Okay. So later we will make precise again this notion. So we'll make precise again this notion. So next is from the previous power series we found, we can find power series for the other cases. Okay. So for example, we want to express 1 over 1 plus s squared in terms of sum of power series, and then find the interval of convergence. So how do we make full use of what we have known? Okay. So one trick calculus always do is substitution. change of variable. Okay, so we already have a basic form of 1 minus x. So how does this 1 plus x squared looks like 1 minus x? Minus minus. Okay, so you make it into a 1 minus x squared. Okay, so you do this change of variable. Then, from what we know, this will be becoming 1 minus x squared to the power n. Right? Okay, so which is just infinity and then minus 1 alternating some sign to the power 2n. Okay, so this is the power series expression for the new function here, 1 over x squared, 1 over 1 plus x squared. So what's next? So when does this converge? Okay, so when does this converge? Since you are using the power series of 1 over 1 minus x, right? So it is bounded by the condition here. So when does this converge? When x is less than, when the absolute of x is less than 1. Okay, so this means that this converges for the absolute of x minus x squared less than 1, because you sub x to be minus x squared. Okay, so which implies that x squared is less than 1, which implies that x squared is less than 1, and then also x is less than modulus x is less than. Okay, so you still stay the same range for this case. Okay, let me see if there's anything special here. So maybe you can try for these two example as well. So do the same thing. So for this left for homework question, right? If you find it very hard to understand, you can message me, email me, and then we will bring out in the next lecture. Okay, if it is easy for you, then very good. Okay, then we can move on, keep moving. Okay, if you think that it's very hard to understand, you can bring it up, and then we will discuss in front of the class again. Okay, make sense? Is that okay? Yeah. So usually the one I left as homework, right, is the same principle. You just use the same way to solve it. Yeah. Maybe a little bit trick, but not too hard. And I also will release it as a after class note. Okay. Any question? No. Yeah. So please do assignment. Okay. Don't left to the last moment. Okay. Yeah. If you have question on assignment, you also can come and find me. You can discuss with your friend, but don't copy. Don't copy answer. Where's my attendance list? Does everyone sign? Okay, thank you. So we'll see you again next week. Thank you. So the office hour, if you want to talk about project stuff, you also can do so.
So,
Yeah.
where should we write the answer?
Where should we write the answer?
I should crop this and insert the
Up to you.
answer here, or just
Wait, you want to type or you want to write?
Type.
You can ignore the question anyway, anyhow, as long as it's easy to read. Yeah. You can just write the answer also can. You can use my text file and then write below it also can. Just anything that's readable.
Okay.
Partial derivative. Wait.
Because our ODE already changed to
Yeah, because we are learning exact and we we don't do because the all these stuff. Wait. Wait. Let me close this stuff first. Stop the recording.